annual physics colloquium. Dr. Lakshmi Raman was in fact an alumnus of the physics department here. She did her master's at the Queen Mary's College, Chennai, and did a PhD in crystal dynamics in the Department of Physics here. She then went on to do her postdoctoral research at Max Planck Institute, Stuttgart, at ETH Zurich, and at the University of Texas, Austin. She then moved on to the private sector, where she had a long association with Bell Core. Maybe many of us know that as Bell Labs. She worked extensively in the field of telecommunications, in the area of network management. She was an internationally recognized expert regarding standards in telecommunication. And more than anything else, throughout her career and life, she had a keen interest in the higher education of women, and often volunteered teaching of high school women students. To honor her memory, her family has kindly sponsored the annual Lakshmi Raman Memorial Lecture, where we invite an eminent female researcher in the field of physics to give this lecture annually. It's now my pleasure to introduce the speaker of the evening, Professor Barbara Terhal from the Delft University of Technology and QuTech. Barbara obtained a PhD from the University of Amsterdam and then worked as a postdoctoral researcher at the California Institute of Technology and at the IBM Watson Research Center in New York. In 2010, she moved back to Europe with positions at RWTH Aachen and at Forschung Zentrum Munich. Since 2017, she has been a professor at the Faculty of Electrical Engineering, Mathematics and Computer Science at Delft and a group leader at QuTech. For those of us in the field of quantum information and computing, Professor Barbara Terhal needs no introduction. She has made several pioneering contributions, starting from her PhD thesis where she came up with the concept of entanglement witness, to quantum information protocols that many of us may have studied or worked on, such as remote state preparation, information locking, exploring the computational power of stochastic local Hamiltonians, and so on. Her current research interests include quantum error correction and fault tolerance, with applications to superconducting quantum processors. On a personal note, I would like to add that Barbara has been a role model of sorts back from my PhD days, and not just for me, but for many of us women researchers in the field of quantum information and quantum computing. So it's indeed a great sense of déjà vu to be able to host her here and have her with us today. So let me now invite the speaker of the evening, Professor Barbara.
Thank you, Barbara, for such a nice introduction, and thank you for inviting us to be here and spend a few months at, are we okay? Yeah, at the IIT Madras, and for me to give this lecture. Yeah, so as Barbara said, I've been interested in quantum error correction and fault tolerance with particular superconducting qubits, because that is a platform on which we want to do quantum computing that is pretty far advanced. And if you want to do quantum error correction, you need a couple of quantum bits. But so what I'll do in my lecture today is I'll give you a little bit of a flavor. Well, what is a quantum bit? What are multiple quantum bits? What are the errors on quantum bits? So what's my enemy, sort of, and particular, sort of how does this work for superconducting qubits? Of course, this will be a little bit superficial, and if you want to know more about maybe superconducting qubits, you can also go to the lectures that David will give. It's a bit noisy here, so maybe I should move further away. So the lectures that David will give later, and I will also give a few more lectures on quantum error correction later in March. All right, so now let's get started. We had an IIT here. Oh, wait, I have to do this. Yes, we had an IIT here, and I'm going to start with something very basic. Any engineering is fault tolerant, meaning that some stuff never works perfectly, right? So if you just imagine, which I sometimes do, I like fixing problems at home, like electrical wiring. If I imagine that copper didn't bend so well, I'd have a much harder problem fixing an outlet or stuffing the wires in there. And it's clear that, you know, the copper wires are never quite, or if the copper wires instead of copper wires, they would be stiff and didn't bend at all. I mean, I don't even know how we could have all the electric circuits wiring that we had. And so that is, in some sense, an idea of fault tolerance, meaning that the thing still has its functionality, even though there are errors. There's rain, there's humidity, there's bending, etc. And this seems like a very obvious principle that anything that we build needs to be robust to errors, infrequent though they are sometimes, like tsunamis or whatever. But for quantum bits, we have to start from the beginning. That's to say, we start with objects, quantum bits, that are extremely fragile. They're extremely sensitive to errors. They're not at all fault tolerant. And we somehow have to work ourselves to something that we can call sort of robust. And this is basically, I say, what's going on in the field of quantum computing. And I know there is a world out there of business in which they talk about a computer, and it's very much hyped. And I feel like this is a very wrong picture to have in some sense, because we can't think about any applications really if we don't have a computer. And I don't call an experiment with 10 or 5 noisy qubits a computer. That is a quantum experiment with fragile quantum bits. So it's early in the field, and but we're making interesting progress, and I would like to also allude to some progress that has been made in the lab, not by the group that I work with, but by other groups worldwide. All right, so I have to do this. Okay, now, wait a moment, this is the, yeah, okay. Right, so here is on the left, you see a paperclip, which is another very fault-tolerant idea, right? The paperclip keeps its function, even though maybe the metal is a little bit bent. And on the right, you see a representation of a quantum bit. So a quantum bit is, you could say, is a two-dimensional vector in a two-dimensional Hilbert space or a vector space, and we're represented by its Bloch sphere. So what we have is we have a unit vector in 3 dimensions, and we call the North Pole 0, we call the South Pole 1, so that's my 0, my 1, that's my bit. But beyond these 2 states, I can have any state, any vector of unit length I can make and I can manipulate. So operations, logical operations on this quantum computer are, say, I rotate this vector. Right? If I rotate, 0 to 1, it's a classical operation because it's just like a bit flip, but I could also do, half a rotation, and I rotate the 0 to, say, something like the equator. And so I describe this quantum bit with 2 real parameters, and then you can say, okay, what are the errors on this quantum bit? Well, if I leave it idling, then there are sources in which this quantum bit sort of loses its state. And these are usually characterized, I'll come to that in a moment, as dephasing and relaxation, and they maybe have error rates of 10 to the minus 2 or 10 to the minus 4. Okay, I'll come to more details later. Okay, so the point is that all logical components that we want to do on this quantum bit will have errors, and let's look a little bit at how this works for the for superconducting qubits. Okay, so so the most popular qubit to date, I would say, is what's called the transmol qubit. It's an invention by a team in Yale in 2008. And it's something that you could see as an electric analog of a pendulum, a swinging pendulum. So if the pendulum swings only very lightly, you could approximate this pendulum with an oscillator, a harmonic oscillator. And if you've had some quantum mechanics, then such a harmonic oscillator can be quantized, and it has equally spaced energy levels. If you'd have such a harmonic oscillator, I could call the lowest 2 levels, the lowest level I could call a 0, and the second level up I could call a 1. But as you know, there will be many more levels. All right, but if the oscillator is slightly anharmonic, which it is in this sort of electric analog, there is these levels are not equally spaced, which help us a little bit because actually we want to do all our operations while the qubit stays in this 2-dimensional space. So maybe we want to drive 0 to 1 by sending in microwaves, because actually the energy splitting of this qubit, this transmol qubit, is about 5 gigahertz. So this is microwave frequencies. But we don't want this qubit to get excited to higher levels. All right, now I said it's just an analogy. What is there's a mechanical analogy of a little pendulum, but now maybe you want to know more about what is actually this qubit. And then there's either some sort of, circuit diagrams. So one way of seeing this is that, okay, so if you have the sort of the electric analog of an harmonic oscillator is inductance in parallel with a capacitance. So basically, instead of kinetic energy switching to potential energy, you get magnetic energy sloshing to electric energy and vice versa. right? So these are elements that can store electrical energy or magnetic energy. But in our case, we don't have a harmonic oscillator. We actually have something that can be modeled as a nonlinear inductance. And this nonlinear inductance in practice is formed by a very tiny thing. So if we look at this is a picture of a chip. So these two white things are interdigitated. These are two pieces of superconductor, aluminum, and they're sort of interdigitated because they want to have a large capacitance. So they want to sort of be close to each other. But then there's a little unit over here, and that is zoomed in here, and that is further zoomed in here. So this is, say, the same material. And this little thing is 100 nanometers wide and a few nanometers thick, actually, is the Josephson junction. So there is a piece of aluminum here, a piece of aluminum there, and there's an oxide, which is a few nanometers thick. And that is a junction through which Cooper pairs that are present in the superconducting condensate can tunnel. And then, okay, so this is a very small unit, and often you have actually something where there's another Josephson junction here, and this is a loop, and you can apply some magnetic flux through the loop, and that's depicted here. This little box is the Josephson junction. It's another Josephson junction, and then there's a loop through which you can apply, let's say you pass a current by, that will apply some flux through this loop, and it turns out that applying that flux through the loop changes the frequency of this oscillator. So it changes the energy difference between 0 and 1. So it changes the spectrum slightly. And that is sort of a control knob that's used to also, do things with this qubit. All right, so this is a very small structure. It's hard to fabricate, so it's a very much like, it's a fabricated qubit, and it's very different from qubits that are made out of atoms or ions, because this qubit, every qubit is different because it depends sensitively on this a few nanometer thickness oxide, which is very hard to make very uniform. And then, there are other sources of noise also around. All right, so we want to use these two states. Okay, so. Yeah, so what we have is that we said 0 and 1, those don't have the same energy. So if I prepare a state on the equator, some superposition of 0 and 1, I'm starting to persist, right? I'm starting to rotate, and I'm rotating at a frequency which is about 5 gigahertz, right? And now one of the issues is that maybe this rotation speed is slightly changed by some noise or some, coupling with some external thing nearby, and I'm sometimes rotating a little faster, sometimes slowing. So I'm losing phase information by this. That sort of characteristic time over which my qubit dephases, so it loses the phase information, is the phasing time. And for my transmon qubit, this is order microsecond, 10 microseconds. I'm going to be mentioning some energy scales to sort of give a sense of how fast things go. But of course, these things are like, if I say, well, okay, 10 microseconds, it looks like, that's pretty short, not very long. But of course, it depends on how quickly am I doing operation on this qubit. Because it turns out I can do single qubit gates, say moving, rotating 0 to 1 in say order 10 nanoseconds, right? So that's a factor 1,000 faster. So I could pack sort of 1,000 of these single qubit rotations into this time. All right, now there's other sources of errors, which is there's energy exchange with other systems. And so, for example, if 1 is the high energy state, then typically, 1 doesn't stay there indefinitely. There'll be some loss of energy to the electromagnetic environment. And, usually if that is a real thermal environment and we're in millikelvin temperatures, because these qubits are operated on at very low temperatures, millikelvin, then in principle, 1 should decay to 0 and then 0 just stays in 0, because that's really, a very low temperature. So there will be stray excitations. Now in practice, there are actually stray excitations, but okay, so they have other origins that are not thermal. Okay, but anyhow, the characteristic time over which this happens is also order 10 microseconds, and sometimes this can be stretched to milliseconds. And again, this is actually one important aspect of doing operations is that this transmon qubit, the gates that I want to do, so these are rotations of my qubits, or something between 2 qubits, those are actually pretty fast. So those can be done in order 10 nanoseconds or so. But the measurement of a qubit typically takes by 500 nanoseconds. So at least it's an order of magnitude larger. And during a measurement, you know, these qubits sort of fall apart, right? So this is a substantial source of errors when we talk about quantum error correction. And the problem is that the measurement cannot be, it's hard to actually speed this up very much on these qubits. All right, so let's look at, okay, so I already said a little bit about qubit manipulations. So we have this precession on the Bloch sphere. If we leave the qubit alone, this is also an important thing to realize. If you learn about quantum bits already a little bit from a book like Nielsen and Schwang, you say, oh, I need to do this gate and then that gate, and then if I don't do gates, the qubit just sits still. You know, if it's a 0, it stays a 0. If it's something on the Bloch sphere, say this point, it just stays there. That's not often the case. It is actually processing. And what I'm actually doing, if I'm doing these microwaves, say maybe I'm starting with something on the Bloch sphere that's processing, and then I put in my microwaves, and then it sort of processes down to sort of say 1, right? And so it's, you know, that's the sort of motion that is really happening. But this additional rotation is not relevant because I'm only ever measuring, if I do a measurement on this qubit, I'm asking this qubit, are you a 0 or a 1? And a quantum measurement on a qubit like this, it's just a projection. Like, for example, I have this purple state, the state psi, and if I say, qubit, are you a 0 or 1, then it will answer I'm a 0 with a probability that just depends on the length of the projection. And of course, it doesn't matter at all that this qubit is processing around like that for that measurement. All right, so now, as I said before, what we don't want to have happen, I'll come back to that a little bit in other aspects, is leakage. So in this Bloch sphere, the qubit looks like a qubit, but I said it actually is 2 lowest energy states of an anharmonic oscillator. So there are these higher levels. I don't want to end up there because I may not have very good control there. And so these errors are typically called leakage, and so I want to avoid this at all costs. All right. Now, if we have more quantum bits, then if you think classically, you say, well, okay, there's like spinning tops, and they're all sort of, you know, spinning around, and maybe I'm rotating one of them, and I have all these sort of Bloch spheres. But this is not the case. We can have also phenomenon of entanglement. So basically, we should see, if I have 2 qubits, I could see these states, for example, the state 0, 0, when they're both up, or 0, 1, or 1, 1, or 1, 0. I could see them as a basis of states. And I can build any linear combination of these states, and that is also a quantum state. And these linear combinations of states, they're not representable in this Bloch sphere picture anymore. And if I do operations on these linear combinations just by linearity, I do, you know, combinations of each one of these states. For example, if I have a controlled NOT gate that I showed you very briefly earlier, I can do that on a superposition of states. And now if I want to work out how this happens, I just apply the C NOT gate, controlled NOT gate on every one of them. For example, if I do the controlled NOT gate on this state, the controlled NOT is a gate where if one bit or qubit is 1, then the other one flips. So 1, 1 goes to 1, 0. Right, and 0, 0 goes to 0, 0. So there's some logic, and I can also extend that logic to the superposition. All right, but the cause, you know, if I have these basis states, I can take any linear combination of them. In quantum mechanics, we call this superposition, but we just have a 4-dimensional state. If we think about vectors, we have just a 4-dimensional state, and we can have any state in this 4-dimensional space. And some states we call entangled. And these entangled states cannot be written as a product of pure states, of 2 states, each of them on their own Bloch sphere. Right, and the fact that we have also these states is, of course, sort of the cause of the sort of attractive appeal of a quantum computer, meaning that if I have a state of n qubits, then I'll have to, this will be specified by 2 to the n complex coefficients. So this looks like a very, very large space. Now, of course, this is a little bit, you know, is this really large? Because if I have a probability distribution over n bits, this is also specified by 2 to the n probabilities. And it's no way true that if I work with probabilistic computation that is more powerful than what we already can do. So it's not the fact that there are exponential number of coefficients that is actually special. The fact is that these are complex coefficients and I can interfere things. They're not like probabilities, right? They're complex coefficients, so I can do operations by which I can get things like interference. Right, so it's a one step removed from probabilities. All right, so, okay, so what gates can I do? So I said on single qubits, I can do rotations, right? And I'll be having to do certain rotations to get a universal, to get a very general quantum computation. On 2 qubit gates, I can do something like the C0, which I've depicted here, which is this: if this bit is 1, then this bit flips, and if this bit is 0, then this bit doesn't flip. So I add here x plus y for input x and y, and I added mod 2. All right, but now in practice, it's often, and I'll show you 2 examples, that, for example, something like the control Z gate, that is easy to do. The control Z gate is easily related to the control NOT gate. What does the control Z take? It's something like, well, it says the theme says it. If this qubit is 1, then I put a phase on the other qubit if that qubit is 1 as well, right? I apply a Z, a poly Z, if you know what poly Z is, on that other qubit. If this qubit is 0, I apply the identity here. So if this qubit is 1, I apply Z. If this qubit identity, if this is 1, I apply Z. If this qubit is 0, I apply identity. Okay, but you can also think about that as I need some kind of mechanism that if the energy levels is 0, 1 of one qubit are shifted depending on whether this qubit, the other qubit is 0 or 1, then I should get something like a controlled phase. Right, because it doesn't change what, the base is. This is a diagonal gate, but it should be something like that. All right. Now, what actually is done in practice in all the labs that work on these transmon qubits, well, almost all, is they do a control Z gate in another mechanism. And this was actually first done by the person that I collaborate with a lot in 2009. And this is something here, what you see here is energy levels. So we see here 2 qubits, and there's a state 0, 1, and there's a state 1, 1, and maybe there's a state 0, 2, and there's some state 1, 0, and 0, 1, etc. And what is effectively done is that in this gate, we change the frequency of one qubit. Like I said, we can send in flux pulses to actually change frequency. And we've changed this frequency, and that's down along this axis, so to bring it closer in resonance with 0, 2. And in principle, there could be, there's a coupling between these 2 qubits, because like 1, 1 could go to 0, 2, because, you could, gain, you could exchange energy this way. But because, so when you follow this trajectory of 1, 1, you sort of, move it over here, and then you come back. So you kind of change its frequency by a flux pulse, and you come back. And then the state 1, 1 will have picked up an additional phase relative to the phases that 0, 1, 0, 0, and 1, 1 have picked up. And you want that phase to be -1, because that's the control Z. So that's just a sketch of, if you want to know more, maybe you should go to David's lecture, because he probably can cover this. So this takes time, order 50 nanoseconds, but the problem is also that there is a chance that this is sort of an avoided level crossing, if you're familiar with that you sort of fly off the handle, you go from 1, 1 to 0, 2 by mistake because of some noise. So there is some leakage. For example, we did this gate, and it had some leakage probability per when I was doing the gate. So with probability 0.1%, which looks pretty small, we would end up in state 2. Now, another gate, which does have that problem of leakage less, is the I swap. And the I swap is a gate that's generated by this Hamiltonian. Now, maybe you're not so familiar with these polys and so on, at least not in this language. But the idea is that this is just an exchange of energy. And so if I have 2 qubits and they're coupled, then, and in principle, they could interact. But if they're off resonant, means there's energy zero energy splitting of this guy is different from here, then, that coupling will not do very much. Maybe, it will not do very much. But then I could change the frequency of this qubit to bring it in resonance, and then this couple, yes?
H1H2, right?
Yes, sorry, yes, the H2, thank you. So I could bring them into resonance, so then the coupling would be much more effective, and they could change energy. And that exchange of energy is also called a flip-flop interaction. It's sort of like U1 goes down to 0 here, and 0 goes to 1 there, and vice versa. And that is the same as this interaction. And that generates, if I do it for a certain amount of time, some gate that's called the I swap, of which the logic you see here. So just there's an exchange between 0, 1 and 1, 0, and 0, 0 and 1, 1 remain the same because they can't, there's nothing to exchange there. And so the I swap is actually not quite a C0. It's actually some gate which you can write as a C0 plus an additional swap up to single qubit gates. So it has an advantage, it has less leakage, but it's not quite a C0. And I'll come back to that because I'll make the point that in quantum error correction, we'll want to use C0s and control Zs.
That's just the X5 model, two-side X5 model, is it?
Yes, yeah. Yeah, I mean, just 2 qubits, right? It's just, but the point is that this gate has not been sort of used so far for quantum error correction because you have this additional swap. But now we are exploring some schemes where we can actually use the I swap, which maybe has less leakage. All right, sorry. Okay, so measurement. Okay, so then the measurement is another thing. So let me just give you the sketch of the measurement. Okay, I have this sort of nonlinear oscillator, it's my qubit, that's coupled to a resonator, which also has a different frequency. And because they're off resonant, what the effective interaction is something where whether this qubit is in state 0 or 1, changes the frequency of the resonator, right? When the qubits are in 0, the frequency of the resonator is this. When the qubit is in 1, the frequency of the resonator is something else. Now, what happens if I probe the resonator with some microwaves? It's all microwave regime. Then the reflection that I get back from the resonator will depend on the resonant frequency of the resonator. That's just physics, right? But that, resonant frequency will depend on the qubit state. So the reflection will depend on the qubit state. That's basically the measurement, right? And that's a very, very short summary. But actually, you can not only measure, 0 or 1. You could even measure whether your qubit is state 0, 1, and 2. And here's some data to do that. So, for example, this is actual experimental data where there are 3 blobs, and you get a point out of the purple blob if you're in 0, a point out of the 1 blob if you're 1, and a point out of the yellow blob when you're in the state 2. And you see for some qubits there's some overlap. So you see that's a source of errors clearly. Right? But this, like I said, this measurement takes a bit longer. All right. Okay, so this is now the end of sort of the noise. This is actually a chip, like we've made, or the Carlo lab made it, and there's a lot of things. There's these little Pac-Mans. There are the transmon qubits. Then there are flux lines they use for changing the qubit frequency. Drive lines is due for single qubit rotations. Readout lines to send in probe microwave readout resonators to do readout. And the readout resonators are coupled to the qubits to induce these phase shifts. So very shortly, and the thing is, this chip, you see, everything is in 2D and all the lines are on the outside. So this does not look very scalable because you have a bigger footprint, more qubits, then of course it gets way too crowded on the outside, right? This is why other bigger labs have been able to do some kind of integration where all these lines, they come from the top instead. Now here you see data, which, this is sort of what the Google team puts out, where you see so 1Q is single qubit gates. You see a big spread. So these are the single qubit gates that they do in a chip of 105 qubits, and you see there's a mean, and then there's this sort of spread around it. This is their control Z gate. If a qubit's idling, then its average sort of error rate, this is the error rate that's here, so it's about 10 to minus 2. The fidelity of a measurement is also about 10 to minus 2. Let's leave this aside for a moment, but what you see from this, error rates on their chip at least, maybe not on what we do, are 10 to minus 3, 10 to minus 2, and they have some spread, right? That's what we learned from this. All right, so that was a little bit where errors come from, right? So everything we do has can we characterize maybe with some error rates, but now what do we do about it? So quantum error correction is basically, came out in 95, immediately after this idea that we could use a quantum computer to factor large numbers as a solution that really was necessary. Realizing that maybe we could build qubits which I can do these elementary things like a C0 or a rotation or a measurement with an error rate of 10 to minus 3. But then, okay, I do 10 to 3 of these operations and I get complete garbage. So I need to add error correction. So what we do is the following. So a qubit is a two-dimensional, a vector in a two-dimensional complex vector space. A logical qubit is again some two-dimensional complex vector space in a much larger space. Say I make my logical qubit from n physical qubits. So I add a lot of redundancy, which requires also a lot of extra control, of course, which is challenging. Now I say, okay, your error is now discrete or continuous? Because if I rotate a qubit, I can be slightly off, right? I could be, you know, it's just over rotation. So it looks like continuous, like can I correct for this? Now, that's not really true, because if I think about, you know, rotations on the sphere, there, of course, if I can rotate around two, you know, incommensurate, you know, angles, or rotations around two axes, I can generate any rotation. So there is a sort of a basis. Similarly, if I have errors, I can have sort of errors that are generated by bit flips, which I also have classically. And then there are errors that are generated by phase flips. Phase flip, these are just the three polys, x, y, z. And I can see my 0 as 1, 0, my 1 as 0, 1, and these polys as acting on this. And poly y is a product of x and z times a phase vector. Right, so the point is, what we've realized is that if we can correct against x and z errors, we can correct against any linear combinations of them or product of them. And that is actually any rotation. That's a very important insight. But we do need to correct both bit flip and x flip errors, bit flip and phase flip errors, and that is part of the quantum challenge. So let's say a few more things about this. So this is sort of a double trouble idea. So the simplest classical code, so if we think very naively, say, well, what do we do classically? Of course, if I have a 0 or 1, instead of, if I have bit flips, instead of having a, you know, represented by a single 0, I take n zeros. And a 1, I take n1. And of course, if a minority of these bits flip, I still know whether I had a 0 or 1. And I do computation on these states by just doing the computation on every bit that I've copied, right? That's what we call the repetition code. It's very simple. But this is not going to work quantum mechanically. Because this code indeed can correct bit flips, but it cannot at all correct phase flips. Why? Because quantum mechanically, we want to take states like this. We take a linear combination of 0 and 1. So now that becomes this code word, alpha all zeros and beta all ones. But now if I do a phase flip z on any of these qubits, right, let's say on qubit number 1, then this state will go to this state. Right? Because z on 1 acts with a minus, so it puts a phase factor in front. And this is what we call logical change, because what we want to preserve in quantum mechanics, or in this quantum computing, is alpha and beta. And now beta goes to minus beta. And this is bad. And of course, if we were trying to detect errors, so for example, we say, we want to do a measurement, and that's what we're actually going to do. We're going to say, oh, these two bits, are they the same or are they different? I'm not asking you whether they're 0 or 1, each one of the division. I only ask, are these two bits the same or different? You know, and if I have a bit flip on, say, the first bit, then the bits are different, and so detect that. But this type of error I won't detect, because, you know, I'm still, you know, in the code space, so to say. This is a valid state. So this is bad. So the second thing that we have to deal with, so we have to have a genuine quantum code. Repetition code is not like that. The second thing is that we can't just measure, like in the repetition code, say, oh, we take the majority of the bits that we have, and then so we measure everybody. We know we can't measure, if we measure a quantum bit, ask it whether it's 0 or 1, we've lost the information, right? Quantum mechanics has this destructive feature. So we want to measure something about the errors without learning whether we have a 0 or 1 or a superposition of 0 or 1, right? So we want to only get the right information about the errors, and we do this using additional qubits, and these are typically called ancilla or measure qubits. So let's look at that for the repetition code. So what you're actually going to do to detect for bit flip errors, you're going to measure the eigenvalues of these things. Z, say for example, I have 3 bits, I'm going to measure the eigenvalue of Z1 times Z2. And the claim is that on the states, you know, 0, 0, 0 and 1, 1, 1, this eigenvalue is +1, right? Because I have twice, you know, from 1, 1, I have twice a minus, so it's +1. And if a bit flip, if a single bit flip happens, so I do this for Z1, Z2, Z2, Z3, Z4, Z5, if I have more qubits. And so for these states, it's +1 and this is a -1. So this will be detecting errors. And so here, for example, is a figure where I have 3 actually transmon qubits in the experiment, and these greens are ancilla qubits, I have to do these little gates, and these gates, if I do this measurement, it will measure ZZ on these blue qubits. And this qubit, if I measure this, it measures ZZ on these qubits. And if I learn these parities, these are called parity checks. If I learn these parities correctly, I will be able to infer which qubit flips, assuming there's one error or no error, right? Now, of course, if there are 3 errors, bad, right? Because then I could flip all zeros to all ones. Or if there are 2 errors, it's also bad because I'm expecting only 1 error, and then if there are 2 errors, I make the wrong decision, right? So this 3-bit repetition code, it has a distance is 3, meaning that it takes 3 bit flips to map 0 onto 1, right? And it can correct 1 error, and that is usually the formula for that is 3 minus 1 divided by 2 floor, and it uses these intellect qubits. Now, of course, we've learned that these C0s in this measurement also are imperfect. So if we're to execute the scheme, then, well, this information is not reliable. So this whole, repetition may actually make life much worse. This is not necessarily a good idea. It's particular if the noise rates are high. If this measurement is completely crappy, I'm not learning anything, clearly, right? So what I want to do is, first I want to keep on repeating this. That's what it says. So I'm preparing my initial qubits in, say, all zeros, and I repeat this many, many times. And then maybe I measure all the qubit in the 0-1 basis at the end. That's the type of experiments that have been done in the lab, and it's called a memory experiment. So let's say, and I see it a little bit as a game. So the game is like this. So the supervisor of the PhD student who's to do experiment comes into the lab, and he says, I'm going to secretly prepare all these transmon qubits, all the data, not the green ones, but that's a separate thing. The blue ones, I'm preparing either all 0 or all 1. Right, so the logical 0 or the logical 1. Now, and then the PhD student comes in afterwards, and he's going to do these measurements, and he's going to measure all the qubits at the end, right? And the idea is that these measurements, measure these parity checks. And the point is, whether or not the supervisor prepared all zeros or all ones, in principle, these parity checks, if there's no errors, they will not tell you, they will not tell you which he prepared. Right, because they are all, all zeros and all ones are all +1 eigenstates of these parity checks by construction. So the measurement of these parity checks is supposed to detect errors. So now the goal is the supervisor, okay, PhD student, you tell me you do K rounds of this error detection, and you measure everything at the end, and you should tell me whether I prepared all zeros or all ones. That's the goal, right? And the longer the sequence of, longer this repetition is, the sort of harder it gets, because basically, there's more noise that's accumulating, and this error detection is supposed to sort of keep track of, try to sort of, keep track of how much noise there is. Right. So the point is that okay, so you can say, okay, and then whenever the guy says. There's a little bit of a caveat here in the sense in the experiment, actually. If you prepare all zeros, then that's the noise that you have on the actual physical qubit is slightly different than the noise you have for all ones, because ones fall more readily back to 0 than to 1. So actually, this PhD student should say, hey, I'm getting a lot of error rates, so you probably prepared all ones, right? So that's not fair. So we try to actually randomize this experiment to be fair. Okay, so you can ask, what's the probability that the PhD student fails this game if I do D rounds of this repetition and I use a distance D repetition code, so not just D is 3 bits, but scaling. And the point is now, if you look at the data, so here, for example, this is a numerical simulation where I just have a very simple error model where I put errors with probability P in all these gates and operations. Then what you get is something like this. So if this on the vertical axis is the logical error probability, so the probability that the PhD student fails after these D rounds, can we fix this? P is the probability of error. So what you see here, if the probability of error is too high, which is like the kind of, when he does the measurement, what he gets out is kind of crap, then actually the DS9 code does worse than the DS3, right? The red one and this green one and the blue one are all higher. The logical probability is higher. Whereas if P is low enough, the opposite's true. The DS9 case is lower than the DS3 case. So it's clear, in order for this error correction story to work, we have to be on this side in terms of our physical noise, right? This is approximately the noise threshold, and it's about 3% for the repetition code on numerical estimates. And you can argue that this P logical will scale exponentially down in D below the threshold. Once you're below it, and this how it scales down will depend on how close you are to the threshold. It's like a phase transition. So we have to be on the left of the phase transition. And the big news last year was that Google was for the first time on the left of the phase transition. I mean, this is like a summary. They did experiments with a truly error correction code, namely the surface code, in which they showed that for larger D, they get this exponential suppression, which is very impressive. All right, now here, what we show actually here is also a little bit of data. This is also the data out of the same paper because they also run a repetition code on the side, and they go up to distance 25 for the repetition code. And this is the logical error probability per cycle. So this is slightly different as this, but it also goes exponentially down, this exponential scale with distance up to D is 25, and then there's some error floor, which is kind of an intriguing thing, and they don't know, at least what I've heard. They think every hour there's some burst error that I don't quite know the origin of, that actually then introduces a lot of errors that you cannot correct. Right? So that's kind of fascinating that they find this by doing error correction. All right, so actually talking about the memory experiment for repetition code is a very good warm-up for the surface code. That's a code that can correct X and Z errors, but a lot of what we have to do is the same. We have a memory experiment, we prepare, either this state or that state. We have to measure parity checks repeatedly. Then there has to be some PhD student or whatever, and we usually call this person a decoder, that takes all this measurement data, including the measurement at the end, and said, hey, it was a 0, right? He sort of says, I should be, if I prepare a 0, I should be measuring this in the logic, I should call this a logical 0 or a logical 1, right? And that is by itself done by a complicated classical algorithm that's usually called decoding. And I won't go. Okay, so now how we're doing on time?
20 minutes.
Oh, okay, yeah, okay. All right, so now, is everybody good? Because maybe I'm going a little fast, or hopefully, yeah. Okay, so now I want to talk about how do we deal with quantum errors. Okay, so if you believe me that we have to correct bit flip and phase flip errors, of course I haven't really, gone into this so much. And the first thing is that we have to sort of detect these errors. And we'd like to detect these errors similar as for the repetition code, where we say, oh, we just measure a few parities at a time, and maybe the larger qubit consists of many qubits, like this n is very large, and I just check these parity checks at the time. And the reason I like to do that is that, these little circuits, they use just 2 C0s in a measurement, and if I mess something up here, okay, then the measurement may be wrong, and there may be errors here, but it doesn't involve too many qubits. So some of the first quantum error correction codes, they required me to measure, weight 9 or, parity checks that involve 9 qubits. So I had to do 9 C0s. And it's clear that I have to do 9 C0s on this that involve a single ancilla qubit, that by the time that these 9 C0s are done, then probably, the error rate's 9 times worse. So the threshold of these schemes are typically much lower, and we're already, challenged by meeting a threshold as we have like here, 3% or something. All right, so the toric code is nice in this way. So what is the toric code? And so there's a toric code which has periodic boundary conditions, which relates to a torus, and then there's a surface code in which these boundary conditions are removed, and it's a surface. Okay, but what's surface like about it? So what I imagine is that I have my data qubits, my qubits, they are on the edges of a lattice. So every black dot is a qubit. Like if in the repetition code, I could have all my qubits on a line, right? And so, and that sort of surface could be tiling the torus. So for example, this is my, every qubit, every edge here, there's a qubit, and there's a periodic boundary condition connecting this and that, and that, and that. Okay, so now what's my code space? So now I have to specify, I have many qubits, I have to specify some two-dimensional subspace of this Hilbert space, right? Or maybe four-dimensional, because actually the Toric code encodes 2 logical qubits, so it's a four-dimensional space. And the way I specify is that for every phase in the lattice, there is a phase parity check. And it's sort of similar as what I have for the repetition code, except that it touches on 4 qubits. So for the repetition code, it looked just at, 2 qubits. Are you both 0, 0, 1, 1, or are you 0, 1, 1, 0, right? It's just text to parity. That's the only information I get. And now it said, you have those 4 qubits, you have even or odd parity. That's the measurement I do. Okay, and I have to do that for every phase in the lattice. So these actually, there's P, should be F, yeah, phase, plaquette. Okay, phase is plaquette. All right, and then also for every vertex in the lattice, so these sort of, these qubits centered around the vertex, I do another measurement, and I measure also a parity, but I measure it in this rotated basis. So instead of taking like 4 z's, I take 4 x's here. Now, x and z as Pauli's don't commute. So if I say I have to be an eigenspace, +1 eigenstate or eigenspace of these phase checks and of these vertex checks, they better commute, right? So, but then you can observe that every vertex here, say, touches on these 2 qubits, and the adjacent phase touches also on these 2 qubits. So they overlap on 2 qubits, and so they anti-commute on 2 qubits, and twice anti-commutation is commutation, right? Because it's just a minus sign we're getting here. So the point is that all these checks commute, and all these checks have either eigenvalue +1 or -1, so there is a space in which they all have eigenvalue +1, and I call that the code space. That turns out, and I'm not showing you the argument, to be a 4-dimensional space. And that 4-dimensional space, I say, then there are 4 basis vectors, and I call these basis vector this way. This overline is a sort of way of denoting a logical qubit. So this state is a state of many qubits. For the logical qubits, I call it 0, 0. And so if I want to go from this state to that state, I should be doing the logical bit flip on my second qubit. And that logical bit flip will be realized by doing some sequence of bit flips on qubits on this lattice. So I can figure that out. And it turns out, so these are called logical operators. So for example, it turns out for this surface code is that I have to do a logical Z. So I have 2 qubits, so there's a logical bit flip on the first qubit, logical bit flip on the second qubit, logical Z flip on the first, logical Z flip on the second. So those are 4 operations. And it turns out that the Z flips are like, I do a Z on all the qubits on this line, and this line is a non-trivial loop on the torus. And I can also do a Z flip on the other non-trivial loop on the torus, and that is the other logical Z. These I'm just stating as fact, I'm not trying to explain to you. The logical X is kind of the same, but on the dual lattice. So this is a loop on the dual lattice, because now I've changed, faces to vertices and vertices to faces, and edges stay the same, and there's an associated loop. And these anti-commute, Z1 anti-commutes with X1 because they overlap on a single qubit, and these also anti-commute. And these mutually commute because they're sort of actions on separate logical qubits. So I'm generating the whole algebra of qubits just at the logical level. Okay, but the important point is that, you see with the repetition code, in order to map all zeros to all ones, I have to do a bit flip on all qubits. So the distance is n, is the number of physical qubits I have. That's high, which means that I can correct, up to half the distance, basically, right? And the same thing as here. I want the distance to be large, and what's the distance here? It's the minimum weight of these operations. But because, these should be closed loop on the lattice, and that's the essential thing of the toric code, they have distance d. So if I have d squared order d squared qubits, then this thing scales like d because, you know, yeah. Okay, so I have a lot of distance, and what I have to do in terms of the experiment, I have to measure the eigenvalues of these 4 qubit parity checks. And this is sort of local in the lattice, so I can grow d, so similar to the repetition code, I can grow d, and I can keep on measuring this, and I can try to do this memory experiment. All right, so now for the small, okay, so now a small, you know, some colorful slides. So the toric code has these periodic boundaries. Whereas in a superconducting device, I have to do my C0s between qubits that are coupled on a 2D chip. Well, in the simplest scenario. So I'd like something that has boundaries. And that's the surface code. In the surface code, the picture is slightly different, meaning that the qubits now are on vertices of some sort of checkerboard lattice where I have blue checks and green checks. So all the white dots are data qubits. So here we have 9 of them, which makes for distance 3 code. So these are the logical X and the logical Z. You know, before they had to sort of go, you know, there were loops. Now they just terminate at these boundaries. And so I measure with the green thing, I measure the ZZZ, and I do that with a green ancilla qubit that I place sort of in the middle of these guys. And for the X, I do that with a blue ancilla qubit, and I run a little circuit with C0s, which, you know, involves this ancilla qubit and these qubits nearby. Okay, and then I can do a much bigger, and this is actually a picture from this, yes?
How many terms take this?
This has a four-dimensional space, yeah. Right. Yeah. Oh, sorry. This is a surface code. This is one. Yeah. There's only, this is the logical X and logical Z. Yeah. I mean, I don't need to. Let's say I just, you know, one is fine. Okay. So here, what you see here, this is the same thing where the yellow ones, now it's a different color variation. The yellow ones are the data qubits, and there's dark blue and light blue to denote the Z's and the X checks. And here you see this little guy is sort of this patch, and that's a DS3, and the DS5 is this patch, and the DS7 is the whole thing. So they run experiments where they go from DS3, DS5, DS7. All right. Yeah, and so now we can just sort of mention what they've gotten. I mean, you can say a lot more about the surface code architecture. So why is the surface code interesting for now is that it's just, you know, you only need to connect the qubits on this 2D plane, and that's very well adapted to my superconducting chip. Like I showed you that these couplers are all in the plane. They can make some crossovers, but it, you know, it gets more complicated. And the noise threshold, what's numerically estimated, is about 0.75%. But this is a rough number, of course, because it's sort of, this isn't just numerics. It says, oh, let's assume that every 2-qubit gate, 1-qubit gate, idling, measurement, preparation, all have the same error probability, and let's call that P. And what's, you know, when am I on the left of the threshold? What's that point P, right? And so this gives an approximate number. And you see here, if you look at their error probabilities, while the 1-qubit error rate is more like lower than 10 to minus 3, and it has a large spread, and the control Z is sort of over here. So you see, you know, it's all over the place, right? But in terms of the experiment, what they see, so here on the right, you have quantum error correction cycles. So you do, this is the logical error probability. So I'm doing this memory experiment, and this is my graduate student saying, you know, can I still figure out whether you prepared a 0 or a 1? And of course, the more cycles I do, the worse this gets, right? I lose the information of the initial state. I can't keep my qubit alive forever. And so, yes?
In general, you could have different sources of errors. And
yes.
some of them may need correction in a 2-dimensional space and some in a 4-dimensional space. What kind of experiments are happening there?
Yeah, so if you mean so originally I had my transform qubits. I said, oh, 0 and 1 is my qubit, and I could also go to higher dimensional space. So those are called leakage errors. And leakage are indeed, so this code is not designed to correct for leakage. And this has been an issue. And so what they do is they actively try to, if a qubit has leaked, they try to do a certain pulse that if it's out there, it would, you know, go back into the 0-1 space. But where it goes in, they don't know, so it means that it becomes a regular error, but then that regular error can be detected and possibly corrected. Yeah, so I hope that answers your question somewhat, but so...
Is it possible to correct two different sources of errors?
Yeah,
Are they commuting?
Yeah, the point is that in some sense the source of errors doesn't matter. Well, they do try to have a budget in terms of like what error contribution, but it's more like, okay, how much does the measurement error contribute versus the control Z error? So for every operation you do, like a control Z gate, they try to say what's the probability of error if they do the operation. But that probability of error can be different for this pair of qubits, or this pair of qubits, or that pair of qubits. Right? But they try to characterize this, and that's why you get this this spread thing. But what is the cause of error? Yeah, people try to say, oh, maybe it's a coherent error, meaning that's a unitary rotation that's gone off. Or it's not a coherent error. Is it a leakage error? I mean, there's all kinds of error characterization. Is it an error which has a time correlation, which means that it's something that's correlated, it's what's called non-Markovian noise. So, but in principle, it all goes into a big pile of stuff, and there's nothing that says, the only restriction on error correction is that errors are local. And that says that the probability that all these qubits fall apart simultaneously goes like p to the n, where n is the number of qubits. And that is an important point, right? And that's why burst errors are dangerous, right? Because if there's some moment they say, oh, now all the coherence times T1 of these qubits goes down, and that's what they see, that is a thing that you can't correct for. Usually errors are independent. I mean, in these noise models, you assume errors are really independent, and they're not quite independent. There are some correlations, because maybe you send in a microwave tone and it actually, excites a qubit that's not supposed to be excited, and when you don't send in but you send in a microwave tone to drive another qubit, so there's a correlation between driving that qubit and having an effect there. Yeah, so yeah. All right. Okay, and here on the left, on the right, you see also. So you can look at the logical error probability per QEC cycle, not so the probability of error that you do, after all the whole experiment is finished, but just sort of per cycle. And again, this should go down exponentially if you're below threshold. And before I had sort of e to the minus c, and p divided by the threshold. That is a quantity that's less than 1 when you're below threshold, so this should be going down exponentially. That's the kind of behavior you want to see, and that's sort of what they look at here, where you have data points for 3, 5, and 7. Right, so that's sort of the corroboration. Okay, yes, right, that's a good timing. Okay, what's next? So I haven't said very little about my own research. Maybe I want to allude to this now. So I think it's important that more groups actually achieve this type of feat. And as we say in the Netherlands, when one sheep crosses the dam, more will follow. That's what we hope to see. And for example, this was just a memory experiment, right? We're trying to keep a qubit alive, and it's not even, well, the qubit is either 0 or 1. It's not even a superposition of anything. But we don't believe that a superposition would fare very differently. But we also like to do logic. So we'd like to do, on a surface code sheet of, say, DS3, it represents one logical qubit. Now I want to do a CNOT between this logical qubit and that logical qubit. How do I do that? The techniques for doing that in purely 2D, and these have not been shown to be below threshold, and they may be more sensitive to measurement errors, although I expect that this will be done very soon. But then there's also a question about overhead. Right, because it's nice to have all this redundant stuff that we have now qubits, that the bigger they are, the better maybe they are, the longer they keep their state. But it induces a lot of overheads, very complicated experiments, so we'd like to use better quantum error correction codes that may use less overhead. And we'd like to, in general, use optimized coding schemes for the hardware. For example, if we could do quantum error correction cycles, say for the surface code, that use the I swap, then maybe we'll have less leakage. And maybe then this will, outperform what we have right now. So these are kind of engineering type questions where we say, hey, maybe we can just get slightly better by doing this clever thing or that clever thing. So I find this interesting. And so I've been working, for example, with my PhD student on something that lowered connectivity. So there was a recent paper on on these codes that encode many more qubits. So they're called quantum LDPC codes. So the thing with the surface code is you say, okay, I have one logical qubit, is one piece of surface code, right? And now I want that D to be large. So, you know, D is 7, that's 49 qubits or maybe higher. So I have a very low error rate. But I can also say, well, maybe I want to encode K qubits into N. And I want that ratio K over N to be quite high. Right? But I also want that growing distance. And so those are codes that are much more attractive in the long run, in principle, because I can pack many more, you know, I can use my physical qubits to pack a lot more logical qubits. But it's been hard, at least there was no evidence that such code would tolerate the noise rates that we see in the experiment right now. And so IBM had a very nice paper, high threshold and low overhead full-tone quantum memory. Right? So the title says it all. It has a high threshold, so actually it's a code, and I don't know if we see this here. So here they have a code which are called a gross code that you have 144 physical qubits, and you pack in 12 logical qubits, each at distance 12. But now you have to compare. So this is really amazing because you say, oh well, if I had a surface code and I needed to have 12 logical qubits, each at distance 12. So distance 12, I need D square, I need the square of that in terms of number of qubits. So each logical qubits would take me 144 physical qubits. So then times the factor of 12, so I need 12 of them. So this is a factor of 12 less, more savings, right? A factor of 12 fewer qubits. And it can deal with the same, it produces the same logical error rate in terms of merit. But the thing is that this scheme, instead, so in this Google scheme or in the surface code scheme, every qubit has to talk with 4 other qubits in order to do these parity check measurements. So this determines where you put your couplers, and you need to have 4 couplers per qubit. Right? And the fewer couplers, the better, because everything is complicated. So here, this qubit needs C0 cavity with 6 other qubits, so that's the price you have to pay. Can you fabricate a chip like that? In addition, this scheme is actually not completely planar. It's called what they call biplanar. But anyhow, so we've developed sort of a variant of this, where we have actually the same performance as they have, and we have also some new codes, where every qubit talks to 5 other qubits. And this uses some new technique of measuring parity checks that we believe has more applications. And we also, they have shown that for the surface code, in principle, in theory, you can also use the I-swap. So the I-swap is actually, see, the problem with the I-swap is this. If I want to do a C0 gate based on the I-swap, I need to use 2 I-swaps. And 2 I-swaps is an error rate twice 1 I-swap. So yeah, I don't want this. So, because the I-swap is modulo single qubit gate is the same as C0 and swap. So basically I need a scheme that it's okay to be swapping my qubits while I'm doing my gates. And so you can actually integrate this in quantum error correction, and we believe we can also integrate that in our scheme, although we're still sort of examining some aspects of this. All right, I think that's it. Yes, thank you for your attention.
Game.
Yeah.
And you had this error probability versus the, I think the noise probability on the x-axis.
Wait a moment, sorry, let me just,
this one. The p bar versus p plot. So is it possible to gain some intuition for why the scaling with distance is different on both sides of the threshold?
Well, because in some sense, if what you do adds more errors than you take away, then, the little unit you do, you're trying to detect errors. So you're trying to remove entropy, right? But what you do is actually noisy. So you may, you may make things worse. And clearly, if I say, oh, I'm not detecting any errors, and I'm representing 0 by 3 zeros, I now have, and I only look at 1 bit, then of course I multiply my error rate by 3, right? I have more places where errors can happen. But of course, there are different things, right? Of course, at the end I could say, still take a majority vote and ignore this information. I could be doing that. In some experiments, this unit is so poor that actually just looking at this is actually better than trying to decipher what you learn here. Is that helping with the, yeah?
Yeah, I guess I was trying to ask,
Yeah.
what is the trade-off that causes this single point on this axis where all the...
Yeah, of course it is not, okay, so there are finite size effects in the sense that it's not a single point, but it goes to a single point and it goes really to something that is a phase transition. It becomes, you know, sort of like flat here and then goes up. And because the point is that here you're just making what you're doing in your, okay, so what this unit does is tries to learn about errors. Now let's say the noise is bad enough that this is not to be trusted, and you are introducing more errors on the qubits also, right? And that is sort of what happens here. And well, you know, actually, von Neumann in 556 has a nice paper which he explains the repetition codes. He says, okay, I have a process I want to make it robust, so I do it 3 times and I take the majority vote. And then, but now let's say you're very bad at taking majority votes. You make computation errors all the time. Like, how low should the you know, when is this actually better as a new unit to do? I mean, I also sometimes give the example of decode, you know, debugging, right? Okay, you write code, you're bad at coding, so, you know, there's some errors, you're debugging. But, you know, you're so bad at things, you're also bad at debugging, so when you're debugging, you make new errors and you're not figuring out at all what's happening, right? So I mean, this is like a sort of a naive thing, but, right, debugging is supposed to correct the errors. But if you write a little piece of code to check that the code, where are the errors in the code you're running? But if that little code that you write in order to check these errors has also errors, then what are you getting? Right? So there must be a point. You must be low. In order to work, you must be at a low enough probability. Yeah, okay.
Maybe one more question?
Oh, yeah, sorry, yes, yeah.
Thank you for the talk. I just wanted to ask how many number of physical qubits I need to encode those 2 logical qubits in toric code.
Well, so it depends. So this is variable. So the toric code is a family of codes, and so I can. So because it's a lattice, let me just. Wait a minute. This goes this one. Oh yeah, here. So I said like this lattice can be chosen any side, right? This has some sides, and so if I make this a smaller lattice, I have fewer physical qubits and I have a lower distance. Is that clear? So the similar as a surface code, I can take a small surface code. So I need 9 physical qubits, that's the smallest one, and then the next one is 25, so it's 5 by 5 is the next one, so 25, the next one is 7 by 7, and I have a similar number here, and it's not exactly d squared for distance d, it's just, you know, because there's horizontal and vertical edges, and you just have to count that.
So, I mean, for example, when you are doing classical error correction, for example, the 1511 Hamming code, I can essentially store 11 bits of information and protect 1 bit field using just 4 parity checks, just 4 extra bits are required. So, is it possible to do quantum error correction of more qubits using less number?
Yeah. This is what I said as the LDPC code. So usually, indeed, classically, you use the rate of a code, right? You say I have a transmission channel and I want to send k bits, and instead of sending k bits, I send those k bits plus some parity checks, and now so that's my n. So you know, k goes to n. And what I like, of course, I like these extra number of bits to be very small. And so indeed, for these quantum LDPC codes, we also want k over n to be a constant. And we want like d over n to be a constant. So d is the distance. And so you can correct a constant fraction of errors. But the point is actually the good quantum LDPC code. So if you take random, so classically you can take random bit parity checks. So you just have your bits and you take random parity checks. And that's a pretty good code in the sense that, you know, you can very well correct errors. But the problem with quantum codes, good quantum codes, is that I can't take random parity checks because they have to all be commuting. So if I can take the z checks random, but then the x checks, how do I construct them? So this good quantum codes, that's only been developed since 2020. There were several breakthroughs in constructing these codes. But the problem with these codes is if I take random parity checks over a lattice and say, oh, now I have to have these qubits interact with some ancilla, and if I have a 2D chip, that's not so easy. But for other implementations where maybe you have optical connects or routers or whatever, you know, that may be more feasible, or qubits that can move. So, yes?
Yeah, thanks.
Yeah, yes, you have a question?
Just one more question.
Yeah.
Same question.
Oh, okay.
Okay, last one.
Yeah, so you brought up a point about due to unequal energies of the qubit states, there will be precession of the block sphere in general, right?
Due to what, sorry, the unequal energies? Yeah.
Yeah. So is this something you usually keep track of in experiment when you consider pulse timing, etc.?
Yeah, yes, very much. You have there's like a clock that you know, goes around, so to say, and usually we say, well, we do qubits in the rotating frame, so we kind of pretend they're not moving. So we go to a frame in which we sort of, you know, move around, and then, but I mean, like I said, you know, if I do a pulse. Well, I mean, the point is there's a phase offset that you can do and that you can use to do, like in the block sphere, you want to rotate a qubit from there to there, or so you want to rotate a qubit around the x-axis or the y-axis, and that difference is actually a phase in this sort of frame that you keep track of. I don't know if that helps. But this is also how you do things in NMR, you know, in sort of, yeah, because these techniques all have been, originally NMR was one of the earliest realization of quantum sort of computing, and all these techniques have been sort of carried over in these platforms. Yeah.
Okay, let us thank Professor Barbara once again. And I request Professor Lakshmi Raman so Professor Barbara is visiting us for another few more weeks. So if you would like to meet with her, discuss with her, please get in touch with me. And also she'll be giving a couple of pedagogical lectures on bosonic codes. So watch out for the announcement sometime in early May. Yeah, thank you.